everyone, I'm Zoe and I'm here with Zachary, and today we're going to be talking about RML. So, what is RML? RML stands for Register Machine Language, which is the syntax used for programming what we call register machines. So let's say we have an arbitrary machine M. Then, inside that machine, there are four special types of objects: constants, registers, labels, and operators. We are also given a number of commands we can perform on these objects. In this crash course, we'll explain the different objects and commands and how they work, then show you a method used for visualizing a program in RML and work through an example. So first, for objects and commands, we have a constant, or a const as we say in the biz, is just an object with a constant value, so it cannot be changed by our code. Examples of constants would be something like numbers or strings like 17 or the string Zach is awesome. In order to specify that something is a constant object in RML, we just say const 17. In our picture, we represent this with an upside-down triangle. Next, we have registers, or regs. Registers are a bit like variables in that they can store information and can be assigned to different values. In order to specify something as a register, we can say reg A, and we draw it as a rectangle. But registers are only good if you can actually assign and reassign their values. To do this, RML has an assign statement. To use this assign statement, we could say assign reg A to const 6. This just assigns A to 6. You could also assign a register to the value of another register using the same syntax. In this case, both A and B would contain the value 4. Our third type of object is an operator, or op. An operator is like a function. It takes in arguments and returns a value. An example of two operators we can use are plus and equals. The operator symbol is drawn as a trapezoidal funnel. There are three main ways you can use operators. First, if you want to perform the operation but not know what it returns, you can just use a perform statement. If you do actually want the value, we can use an assign statement. Finally, there is test, which functions like an if statement. This just checks if something is true, and if it isn't, then it skips a line of code. Note that none of these support nested operations. Some other operations we can use are read and write, which are input-output ops. Our last type of object is a label. We use labels to split up our instructions and mark start points. We can use goto statements to go to a different label. There's also branch statements which do the exact same thing, and it's unclear why they both exist. A goto statement works like goto label start, which tells the machine to continue executing instructions from the start label. We can also assign registers to labels. For example, we might have a register called continue that we might want to change depending on where we need to go next in our code. In this piece of code, you can see two labels, start and done. The program starts with A equal to 5 and loops through the start label twice, using the assign, test, and goto commands. When B is equal to 7, the program goes to the value in C, which is the label done, and outputs the value of B using the write op. The final tool we use is called the stack. You can think of the stack as a list of values where we can only edit the first value in the list, which we do with push and pop operators. Push will take an object and put its value at the top of the stack, while pop takes the value, removes it, and sets it to the specified register. For example, when we push reg A and then reg cont, the value 5 gets pushed first, and then on top of it, the label done. Now, if we run pop reg B, we take the value at the top of the stack, which was the label done, and assign it to the register B. 5 is now at the top of the stack. Stacks are useful if you want to save old values of registers that you want to reuse later, but set to a different value. Because of this, they're used in recursive procedures like the example Zach will now walk you through.
Okay, now I'm going to show you guys how to calculate factorial recursively. Jason likes to use this analogy of recursion of workers coming into work. So each worker has a boss and a subordinate, except for the base case worker who's at the bottom of the hierarchy and doesn't rely on anyone else. Problem is, each worker has to wait until their subordinates are finished before they can start. So when each worker arrives, they write down what they have to do on a piece of paper so they don't forget it, and then they stick it on their community bulletin board, which is like the stack in this case, and they stack it on top of their boss's instructions. Then they phone in their own subordinate, who does the same thing, and so on until you get to the base case. When each subordinate is finished with their work, they take their paper off the board, and then they tell their boss that it's time to come back in. And this continues until everyone has completed their job, and we have our answer. So here are all the parts of our recursive factorial. To keep track of the numbers we're multiplying, we'll use the register n here. To keep track of the total product, we'll use answer. And to keep track of which part of the code we want to go to next, we'll use continue. we're going to need to be able to decrement by n by 1 to get all the natural numbers, as well as multiply the answer for each n we have. So that'll be here and here. Finally, we'll need to remember to set answer to be 1 in our base case. We're also going to want to preserve n and continue by pushing them to the stack so that we can pull them off and multiply them after we've got them all. With that, I'll show you the code and how it works by calculating 3 factorial. So we're going to start with 5 labels: setup, loop, post, base, and done. In the setup, what's going to happen is we're going to assign reg n to be const 3, and we're going to assign reg continue to be the done label. In our loop, we test to see if the base case is true, which is when n equals 1. Since it's not true, we're going to push n, we're going to push continue, we're going to decrement n by 1, and then we're going to assign continue to be post. Then we'll do this again. We test n is 2 this time, but that's still not equal to 1, so we don't have our base case. So we're going to go push n, push continue, decrement n, assign continue to be post again, and then go through the loop again. All right, the third time, we can see that n actually equals 1. So that means that instead we're going to go to the first thing here, which is going to be go to label base, or our base case. So we go to our base case, which says assign answer to 1. Now we're going to go to continue, which in this case is post, right? Post says pop reg continue and pop n. So that means our new values of continue and n are going to be 2 and post. So now we assign the answer register to be times and answer and n. So basically we're multiplying answer by n, and so we're going to get 2 this time. Now we go to continue, and continue is just post, so we're going to do this post label again. So we pop continue, we pop n, we multiply by 3 this time, and then we go to continue. But notice that in this case, continue is done. So that means that we're done, and we've solved factorial. And so now you know how RML and recursive algorithms work. To learn more about Lisp and our final project, be sure to check out the videos by Josh M. and the Peters. Thanks for listening.